Okay, so today we are looking at the instantaneous center, which is an important point because it's not well understood until you get a lot of practice. But basically, the instantaneous center is only a mathematical tool in order to simplify some problems or in order to actually solve other type of problems. So by definition, the instantaneous center is a point from which the motion of a rigid body is only due to rotation at that instant. So remember that in dynamics, it's like if we take pictures of a moving object, so we're just gonna have a picture at a certain time. So for example, this is not needed, but it's sometimes convenient to use instantaneous center. Let's say you have a bar or ladder, and this one is sliding. So sliding through point A down and point B to the right. So if we take a picture as the ladder is sliding at that instant, there will be one point, which will be the perpendicular to the origin of each one of the velocities, okay? That will give us the location of the instantaneous center. You see that the instantaneous center has no physical meaning because it's not even on the bar. It's just outside. But from that point, the velocity of any point on the bar will be just due to rotation, and actually the omega would be the omega of the bar. And that's what we have over here. The traditional way to solve this problem is, instead of using instantaneous centers, to find the velocity of point C from two different locations, point A and point B, and solve for the unknowns that you have in the problem. However, the instantaneous center must be used when we solve problems of a rigid body rolling, or when you have some problems of gears. So this line here should not be here, but imagine the point of contact between two gears, and then an object which is rolling but not sliding. Now we're going to look into more detail into the rolling rigid body. So here you see this would be like a different instance, but basically I'm just adding stuff to the figure. So you see, since the figure is rolling, not sliding, that means that the motion of the velocity of point P is 0, and that then at that instant it will look like point A is rotating about point P, okay? But we know that the real motion of A here is just translation. So even though the motion of point A is just translation, the velocity, the expression of the translational velocity will be given in function of omega and r, because from point P, the motion of point A looks to be rotational. And that's basically what we are over here, okay? You see, P is 0 because instantaneous center, but the expression for VA is given in function of omega, even though this is translation. It becomes a little bit more delicate once we go to the acceleration. And that's because the acceleration has two components, would be the tangential and the normal. So to give you a little hint now, once we look at the acceleration of point A from point P, you will have one term that will be here A sub A, that will be due to the tangential, but then it should be no normal or centripetal accelerations. So here we go. And we find the acceleration of point A from point P. We do here this. This is the equation A of P plus the tangential plus the normal. So we get the tangential here, and this will be the centripetal or the normal, will be this term over here. And you see basically here that we get to a point where this one has an x component, but it's a y component due to the normal, and that makes sense to the figure. So the function of this term, A sub P, is to eliminate this acceleration. So A sub P actually is the green term over here. So once we add the term, this term on A sub P, we just end up with the acceleration on the y, on the x direction. So actually this term here cancel with the A sub P over here. And again, this is an example for gears. If this is fixed, this point here will be an instantaneous center. And again, this will be a rotating point where the velocity is 0. So basically, to follow the general strategy in solving problems, we can find the velocity of point A from the instantaneous center and from the center of the gears. So this is a traditional problem where we have a disk, which is rolling, or a ball rolling, and there's a bar attached. So in this problem, we know that the radius of the big disk is 0.5 meters, and that the angular velocity is 4 radians per second, and the angular acceleration 10 radians per second. The length of the bar is 1 meter, and we need to find the magnitude of the velocity VB the angular velocity of the body B, the magnitude of the acceleration at AB, and the magnitude of the angular acceleration. So just by looking at the figure, we see that A sub B, this we only have, can only move on the X. So we have a V sub B X component and an A sub B X component, but no Y component, as you can see over here. So like always, the strategy is to find the velocity of one point from two different locations. So we're going to do it here. We're going to find the velocity of point A from point P and from point B. So from point A, Vp plus omega, we get minus 2 because everything is known. We find the velocity of A from point B. We need to be careful. We know that Vb only has one component on the X. Omega AB is unknown. And then this, by simple trigonometry, we can find that distance over here. Okay? Because the distance from here to here is R, and we know this one here is 1. This will be R, so we can find this one, 1 squared minus 0.5 squared. So once you do the calculation, you find the second expression for VB. You equate one to the other. We solve, we find omega AB to be equal to minus 2.31 and VB to minus 3.15. Now we do the same thing for the acceleration, but here we could go directly from point P to point A, but as the first example, before going to point A, we're going to go from point P to point C, which basically is exactly the same as we did here. All right, and then we will go from point C to point A. So we go first to point P, from P to point C. Same as before, we know this term needs to cancel this one, so we only get one term on the X. Now we go from point C to point A, which would be the point over there. And basically we get minus 13.5. All right. So we equate those two relations. So basically this one here to this one over here. All right. No, sorry. So this is, next we need to find expression of point A from point B. So we go from here to here. All right. And this will be this expression over here. Got the calculation, we get AB minus 0.5 alpha AB plus 4.63. We equate the two relations, we solve, we get alpha AB minus 0.885 minus 4. Okay, so what's important over here, let's go back, is that when you do the acceleration, you see that this term is canceling the Y component, okay? So let's say now that you get more experience and you want to go directly from point P to point A. That can be done, but when you write down this equation, you need to recognize that this term here is of P is just going to cancel out this term over here. So just the Y component of this one, but not the X. So if you do the same thing, we get exactly the same thing as before, minus 13.5, which is what we had over here. Okay, so instead of doing these two steps over here, you could just do one like this, but you need to have the understanding that this term will only cancel the term on the Y direction.